All right, general chemistry class. This is Monday, 15th of February. I know that you're all excited because it was minus 25 degrees out this morning. All right, so let's get right to it. For Monday, we are still in the area of kinetics. We're going to finish kinetics on Wednesday. Today and Wednesday, we'll be talking about kinetics. ALEKS chapter 14b, we'll be done with chapter 14. That assignment is due on Thursday night, Thursday at midnight. So don't forget, lab this week is kinetics of the iron iodide reaction. And we have exam 1 coming up Thursday and Friday. So Thursday for the online class, Friday for the face-to-face class. The exam, which I started writing this morning, is all going to be on Moodle, and you will have 70 minutes to take it. Okay, so Monday we have, it's appropriate to do a little bit of despair today, so let's dive right in. Just like teamwork, only without the work. Let's agree to respect each other's views, no matter how wrong yours might be. When people are free to do as they please, they usually imitate each other. Makes you think. It's only a virtue if you're not a screw-up. This is a nice slide for illustrating the difference between accuracy and precision. Precision's good, how reproducible it is. Accuracy is not so good. If you're not a part of the solution, there's good money to be made in prolonging the problem. And finally, I want either less corruption or more opportunity to participate in it. So ends our despair slides demotivations for Monday. All right, so we are in chapter 14 on kinetics, and we ended up on Friday talking about the integrated first order rate law. Now, the integrated first order rate law is this. And what you need to remember about it is that the integrated first order rate law connects concentration at 2 different times, the time it has taken, and the rate constant. Okay, so with that said, this is the integrated second order rate law. You know that rate is defined as the loss of a reactant, change in concentration over change in time, for a reaction that is second order in a component as opposed to first. We set it up this way. This is the rate law. Excuse me. Reaction is second order in A. When we go through the integration, just like we did for the first order rate law, we get this equation. Now, I'm going to go back to the integrated first order rate law. Natural log of concentration at times t of time t over concentration initially equals minus kT. First order rate law has the natural log relationship. The second order rate law has a 1 over concentration relationship. You don't have to memorize this, but you need to know when to use it and how to use it. Any reaction that is second order, 1 over concentration at time t is equal to kT, should be familiar, plus 1 over the concentration at time 0. And for half-life, you'll notice that half-life now has concentration at time 0 as part of that relationship. It is rare to use half-life for a second order reaction. Sometimes happens, but it's pretty rare to use it. Half-life is almost always applied to first order processes. So with this particular equation, that's what we use. 4 things, just like in the first order rate law, integrated rate law. In the second order integrated rate law, we have 1, 2, 3, 4 components. If we know any 3, we can find the 4th. Because you guys are good at algebra. Okay, So for a second order reaction, here's just an example. Notice what, if you plot, remember when we did time, concentration, natural log of concentration. For a first order reaction, if we plot time versus natural log of concentration, we get a straight line. For a second order reaction, and we take natural log, we don't get quite a straight line. There's some curvature in it. If we plot time versus 1 over concentration, we will get a beautiful, lovely, impeccable straight line that looks like this. All we're looking for is a linear relationship between time and some function of concentration. For second order reactions, that function is 1 over concentration, or the reciprocal of concentration. Okay, so here's an example of data, the data that just went into the plot that I just showed you. Here's time, concentration, natural log of concentration. That gave us the line with a little bit of curvature, and then this gave us that beautifully straight line. Excuse me. I think it's the cold weather. All right. So let's consider this reaction. A goes to products. So here we have initial concentration, K, time, and we're asked to find the concentration at some time down the road. This is concentration of A at time t. So how do we calculate this if we assume the reaction is first order? It's time for my daily fight with the screen. All right. So for if it's first order, we know that the reaction is natural log of so we just plug in the numbers. This is 1.0 molar. We have to assume this is reciprocal seconds. 1.0 times 10 to the minus 2. And remember that the units of K will change depending upon if it's first order or second order. So then, after 30.0 seconds, now there's only one thing we don't know. That's the natural log of concentration at 30 seconds. So if this is 0.01 times 30, this gives us minus 0.30. Units cancel. It's my calculator here. So we have 0.3, and that becomes 0.09. Either the x, either the minus 0.30, 0.09. Just gonna add it in there for pleasure, for fun. Okay, so the concentration, if we're starting with 1.0 molar, that's it. So if it's first order, the concentration of A times T is 0.09. Okay, I'm going to call it 0.9090. Just because I guess we should be sticking with it. Okay, how are you doing with that? Pretty straightforward, I hope. Lovely, glad you got it. Now, What do we do if the reaction is second order? Calculate A after 30 seconds have passed, assuming the reaction is second order. I'm going to back this up just to make sure I have the equation right. Yes. Okay. So this is the term we're looking for. So this is equal to 1.0 times 10 to the minus 2 times time plus 1 over 1, which of course is 1. Now this is equal to this times that is 0.30 plus 1 equals 1 point. So 1 over a at time t is equal to 1.30. I would just take the reciprocal of that. .769. 0.77. For a second order reaction. So all we're doing is using these equations. They have been derived. They're there for you. You don't have to memorize them, but you need to know when to use them and how to use them. Okay. Let's go back to this reaction. Now we've used it before. I just want to go back and show you how do we do this? How do we look at this reaction given this data, given these numbers, and determine whether it's first or second order. If it's first order, time and natural log of concentration are linear. If it's second order, time and 1 over concentration are linear. So we can have this, and by the way, this is where using a spreadsheet really helps, because all you have to do is enter these numbers, enter one formula here and one formula here, fill down the spreadsheet, does all the work for you. Let's pause before we start. Is the gap between these the same? So the gap between the time measurements is the same. 100 second increments. What about concentration? This is 0.31. The gap here is 0.27. The gap here is 0.22. So you see the gap is narrowing, or concentration, or the rate is actually slowing down the further along the gap. So we know it's not zero order, which is what it would be. Zero order is when time and concentration directly are linear. So if we take the natural log of each of these numbers, we get these here. If we take 1 over concentration, we get these numbers. Remember, this is not 1 over log. This is 1 over the original concentration. So let's pause here. Let's look here first. Is it second order? Because here we're looking at some fairly simple numbers. The gap is 9, 50 to 59, 9. 59 to 70, that's 11. 70 to 83 is 13. 9, 11, 13. The gap is increasing. It doesn't look like it's second order. What about here? The gap is 0.17. Here the gap is 0.17. Here the gap is 0.17. Here the gap is 0.17. So do you see the picture? The gap between these numbers is the same, just like the gap between the time measurements are the same. So now we know that we have a linear relationship between time and natural log. And so if we just spread these numbers, the number here is the gap between the first two data points. This number is the gap between the second and third, the gap between the third and fourth. You can see how the gap is changing. The gap stays the same. The gap is increasing. And if the gap's increasing, that means that our slope is changing. And therefore, you can determine whether it's linear or not. So this reaction is first order on the basis of these numbers. So just revisiting that reaction, this is what it looks like, a plot of concentration versus time looks like. And we showed you that it was decreasing. This is the linear relationship between concentration, time and natural log of concentration. And then this is the relationship between time and 1 over concentration, clearly not linear. Okay, so we're done with the integrated first and second order rate laws. The next step is this beauty, the Arrhenius equation. The Arrhenius equation is used for looking at a reaction at different temperatures. So far, everything we've done, what have we been looking at? We looked at rates of reaction, concentration versus time. You can find the rate of a reaction between any 2 points, rise over the run. You can find the rate law from initial rate data, and we did that in class on Wednesday and on Friday. We've looked at using the integrated rate law for first order and second order reactions, and we can determine whether a reaction is first or second order. The vast majority of reactions are first or second order. That's why we don't go any further. We don't really talk about the 0 order reactions or third order, because those are extremely rare. For the Arrhenius equation, what we have here is we're looking at how the rate constants change at different temperatures. Now remember that for a given reaction, we have a rate law. Rate equals K times gets me every time. So here we have the rate law. If it's first order in A, then it's simply, the rate law is simply this. K, the rate constant, can change depending upon temperature. The exponent always stays the same. It doesn't matter if the temperature changes. Whatever the order of the reaction is in a particular reactant, it stays the same. So if M is 2, if this is a second order reaction, it will always be second order for that reaction. The reaction is not going to change the way the molecules react if the temperature changes. It's going to change how fast it goes, but not the mechanism by which that reaction occurs. The rate law stays the same. Rate equals K times A to the second power. Now, as we change temperature, as we heat it up, as we raise the temperature, the molecules are moving faster. The average molecular collision happens with more force. Therefore, the rate of the reaction increases. If you increase the temperature, you always increase the rate of reaction. So this equation, the Arrhenius equation, is beautiful. By the way, this is the same Arrhenius that we talk about in Gen Chem 1, Svante Arrhenius. late 1800s, did a lot of his work. He's the one who gave us the definition of an acid being hydrogen ion and a base consisting of a solution of hydroxide ion. H plus and OH minus, acid base. That's the Arrhenius definition, same do. All right, so we've got this equation now that connects rate constants at different temperatures. These are the two different temperatures, and these are the rate constants. Well, you can see that. And then these are the rate constants. R is the ideal gas law. This time R we're using the unit of joules because E sub A, which you know from the reaction profile diagram, is activation energy. This is a powerful equation because of this. It gives us a way to calculate activation energy, and you will be doing this in lab next week. We're going to, next week in lab, we're going to carry out the reaction of iron, Fe3 plus, and iodide, I minus. You're going to establish the rate law. You're going to find the exponents, in other words. And then once we know what those exponents are, you're going to calculate K at room temperature. Then what we're going to do is warm those solutions up and run them again. And when we run them again, the value of K changes. The rate law stays the same, except for the value of K. So we're going to get like 3 values of K, and we can solve for the activation energy. So let's take a look at this. Here we have 3 different temperatures, 3 different K values. Determine the activation energy for the reaction. All right. Just going to write over this. So natural log of, let me go back to the equation. K1 over K2, T2 minus T1. ln K1 over K2 is equal to E sub A just go one more time to make sure that there aren't any negative signs that I'm omitting. Nope, that's correct. All right, now what I can do is plug in any of these data points, any 2 of the data points, any 2 K values, any 2 temperatures. I'm just going to do the ends, the highest temperature and the lowest temperature. So I'm going to call this K1. We'll call this K2. This will be T1. This will be T2. Plug those in. Natural log of K1, 2 times 10 minus 4. All over K1, K2, which is this guy, 1.1 times 10 minus 4. This is equal to activation energy over R, which is 8.314 joules per mole K. We're going to erase this to give me a little more real estate. Times 1 over T2. This is T2. Do you see why it helps? Notice what I did. I physically labeled which one was which. 1 and 2. I would urge you to do that whenever you have a problem like this. Write down what those labels are because it's easy enough to get these things twisted around. 1 over T2, that's 625. 1 over 625. That's kelvins minus 1 over 645. All right. Now, all we have to do is solve for each thing. It's the only thing that we don't know. We know we have 1, 2, 3, 4, 5, 6 components. R is always a constant, so there are only 5 that are possibly changing. we're either looking for activation energy or we're given the activation energy and then asked to find one of the other components, usually one of the K values. All right, so let's find out what all this mess is here with the temperatures. 625 over X, 0.00 sub A over E.314. By the way, this is 1 over K. Our units here are 1 over K. Units are 1 over K. This is 1 over K, so K cancels. We're left with joules per mole. 0.0016 minus 645 over X. 0.00155. Zero. 6. This is 1610. Okay, so we end up with this number equal to 0.1234496. And this is equal to, do the left side. 10 to the minus 4 divides out. We're left with 2 divided by 1.1. 2 divided by 1.1. Natural log. 0.598. In other words, this mess, 0.5. This is equal to 0.598 is equal to this. So E sub A, we multiply both sides by 8.314. This becomes 4.97 equals E sub A times that. So I divide by 4, 6. And I get 100,000 210. That is joules per mole, or just joules for the reaction. And this is 100.2 kilojoules. That's it. That's all you do for finding activation energy. The trick here is just keeping track of all your numbers. 2 numbers that are involved for your K1 and your K2. Often these are small numbers, sometimes they're a little bit bigger. Natural log of that ratio, don't forget this is 8.314. This is not 0.08206. That is the liter atmospheres one. And then these are always temperatures in kelvins, always. Always Kelvin temperatures. So this is it. This is the answer to the problem. And 100 kilojoules is about right. Remember that this is the energy barrier that the reaction has to overcome in order to proceed in the forward direction. So this is E sub A, activation energy. And it's usually given in kilojoules. Remember, units are joules here, that factor of 1,000 matters. Okay, wonderful. Now, this is what we just did our calculation on, the activation energy. And this is a slide that we've shown you before. Reactants, products, activation energy, transition state. This is the point where the molecules can go back down the hill. This thing, it's not really a molecule, this thing can go back down the hill forward, or it can go down the hill the hill forward or back down the hill where it came from first. Energy profile, reaction, energy profile, they're all the same. Here we have a reaction profile that's a little bit different, just a little bit different. Notice that we have two humps rather than one. It's not just one transition state. This is the activation energy. The activation energy reactants. It's got to overcome this big barrier. And then it falls into this hump. And this is something that's made that is temporarily stable. It's not very stable. It doesn't want to live that way. But it's, think of it this way. It's like two things come together. They overcome the energy barrier, and then they kind of stabilize. Maybe they twist a little bit. That's the intermediate. The intermediate is transient. It's temporarily formed, but doesn't want to stay that way long term. Can't live that way permanently. So what happens then is it continues to go forward and then goes on to products. If we start with products, we go from products, and if we're going back in this direction, well, keep in mind, here's a second activation energy as we're moving forward. We start with reactants, big energy barrier. The small energy barrier that we see here is usually pretty easily overcome. If for something that looks like this. Sometimes the energy barrier here is smaller, this hump is smaller than this hump. In which case it's easier to get here, but harder to overcome that second barrier. So why does all this matter? Because we'll get there in a minute. Okay, what is a catalyst? Now we're going to define one more term. So what have we talked about? We've talked about the reaction profile. We've talked about the transition state, the thing that you have at the top of the hump. We've talked about the intermediate. It's formed temporarily, and then it goes on to react either forward or reverse. Now we're going to talk about a catalyst. A catalyst is something that speeds up a reaction, but comes out in the same form it went in. Sometimes you'll see a catalyst defined as something that speeds up a reaction without really getting involved. Well, the reason it speeds up a reaction is because it does get involved, intimately involved. It's directly enabling that reaction forward. So in this particular case, this is a reaction of A and B that is a regular reaction with no catalyst. This is the same reaction with a catalyst, and notice what happens. It's exactly the same, it's just that the activation energy is smaller. So a catalyst speeds up a reaction by lowering the activation energy. Did you get that? Did you write that down? Take a moment and do that. A catalyst speeds up a reaction by lowering the activation energy. Think of it this way. Let's say we have A and B. They've got to collide with enough force and at the proper orientation for products to be made. But what if we have a surface? A comes down, settles on the surface. Doesn't take long, maybe. B comes down right next to it. Now all of a sudden, A and B are on this same surface right next to each other. Well, they can just kind of make that connection and then move on. Okay, I just thought of about 3 bad analogies, and I'm not going to go with any one of those. But anyway, that's what a catalyst does. It provides a way for the reaction to occur in a lower energy fashion. Now, remember this gap? What is this gap? The difference here, the energy difference from here to here. This energy gap. Remember that? That's right. That is enthalpy. That is delta H for this reaction. Has the enthalpy over here changed? Nope. Remember, delta H, it doesn't care what path you take. All that matters is the energy difference from reactants to products. If we've got the same reactants and products, it'll be the same delta H. So a catalyst doesn't change delta H, it changes the activation energy. All right, now we're getting into the final plunge, the final steps of kinetics. And we're going to wrap this up partly because we have the time. So I want to talk about the kinds of mechanisms that we have. This slide is not as important as some of the others. It's just to introduce you to individual reaction mechanisms and elementary steps. We're called elementary steps. A unimolecular reaction is where one thing falls apart. It would be first order. A bimolecular reaction requires two things. That is second order. A termolecular reaction involves three things. Think of this as like a metal surface with two oxygen atom 1 coming here, oxygen atom 2 coming right next to it, and then they react. A termolecular reaction, third order. Now, let's talk about these definitions. This is an important slide because this lays out some key terms. A mechanism describes the route that a chemical reaction takes at the molecular level. This is usually a set of steps. You might have, the first thing that happens is you collide and you form this thing, which might be an intermediate. Remember it would be the valley between the two humps, the intermediate. The first step would be making the intermediate, and then the second step would be that intermediate moving on to form products. So the mechanism is a series of elementary reactions. Together, the elementary reactions add up to give you the overall reaction. An intermediate is formed in one step and used up later, and a catalyst, it speeds up a reaction. It starts at the beginning, and it comes out at the end in the same form. That is the catalyst. So let's take a look at this mechanism. Take a look at this mechanism. The first step, A and B form C. Once we have C, C reacts with one more A to form D, and we get B back. So what is the overall reaction? Still have Arrhenius here on board. Take care of that. All right, so when we're going to do that a lot, don't I? So, well, that's the next thing. I guess that's what it is. So we have A and A, all told. The overall reaction, A. Everything on, you add up everything on the reactants, everything on the products. So we have 2A plus B plus C goes to everything on the products. C plus B plus B. We subtract out everything that is the same. We have 1B on the left, we have 1B on the right. We have 1C on the left, we have 1C on the right. Our net reaction is 2A goes to D. That's not hard, right? This is the overall reaction. We simply add up all the steps of the reaction mechanism. Elementary step 1, elementary step 2. These are individual molecules and individual species that are involved in the reaction. So let's go back to our definitions from before. Remember this? You're looking at the mechanism. What is an intermediate? It's formed in one step, and then it's consumed later. It's formed early, and then subsequently gets used up. A catalyst speeds up the reaction without being consumed itself. Now what that means is, it starts at the beginning and ends. So, and it's there at the end. So what we have here is C that is formed and then used up. C is an intermediate. We form it here, we use it up here. What about B? Is B an intermediate? No, B's there all along. B's here at the beginning, B is here at the end. B is a catalyst. And a catalyst does not appear in the overall equation. The catalyst generally doesn't appear unless it's in the, if it's not in the overall equation. Okay, what happened here? For this slide, let's just identify some key terms. This is elementary step 1. This is elementary step 2. This is the 2-step mechanism. It's a mechanism because these are 2 elementary reactions. We add them together to get the overall reaction. That's this thing right here. The way you recognize an overall reaction, you'll usually have a line under the last step of the mechanism. So the overall reaction, 2 elementary reactions. Do we have any intermediates that are formed? Anything that is formed in one step and then used up in another. If we have any intermediates, it'll be either this, or both. We form NO. Does this get used up in this step? No, we end up with NO in the overall reaction. This is not an intermediate. It's formed in one step, but it stays. It's not used up. What about this? Is this an intermediate? Take a good look. It's formed in this step, and then it's used up down here. So NO3 is an intermediate. There are no other intermediates. Do we have any catalysts? Something there at the beginning and at the end that's not part of the overall reaction? The answer is no. There's no catalyst. Okay. Given this information, you can write the rate law. So here we have the overall reaction. We never write the rate law on the basis of the overall reaction. What we can do, however, is write the rate law for the slow step of the mechanism. The first step is the slow step. That's what they tell us here. You can't have an overall reaction go any faster than the slowest step. So if this is the slow step, we can write the rate law on the basis of the reactants for that slow step. So the rate law for the reaction is equal to K. By the way, here's what we typically do is for an elementary step, we call this K1 and K2. The first elementary step, the second elementary step. They will have different rate constants. We know that this is, since this is fast, K2 is probably much bigger than K1. So the rate of the reaction, we always write the rate law for the slow step in terms of the reactants. The rate is equal to K1 times the concentration of these 2 NO2s. And that's it. If we know the mechanism for the reaction, we write the rate law from the slow step. That's it. That's it. This is the overall reaction. If we were to have written the rate law on the basis of the overall reaction, it would be one of these and one of these. But that's not how it works. It works by these 2 guys hitting each other, form these intermediates, one intermediate and one product, then the reaction will continue fast. This is a perfect example of a reaction that is second order in one component. And notice, even though the coefficient in the overall reaction is only 1. So these are the elementary steps visually. And I think what we'll do is end here. Take a look at this. Write the rate law. We have 3 steps in this mechanism. We have 3 steps. This is fast, this is slow, and this is fast. So we always write the rate law on the basis of the slow step in the mechanism. We write it on the basis of this guy right here. So we have N2O2 and H2. Let's see, rate is equal to K, K2. Is equal to the concentration of N2O2 and H2. You got that? We have a mechanism with 3 steps. We find the slow step, and we write the rate law using the 2 reactants that are part of that. This is also where, if any of these coefficients is something other than 1, those coefficients become the exponents because these are elementary steps in that reaction. This is all fine, beautiful, rainbows and unicorns, except we have one problem. We have to compare this to the overall reaction. Let's write the overall reaction. Remember the overall, how to get the overall reaction? We had all the reactants together and all the products together. So we have 2NO. Can you see this okay? I'll assume that's a resounding yes. N2O2 plus H2. Here's an N2O. And here's another H2. Those 2. N2O2. N2O. 2, that's a 2. N2O plus N2 and then 2 H2Os. Is there anything that's the same on both sides of the equation? Yes, we have N2O2. So those go away. N2O. N2O. So our overall equation looks like this. 2NO plus 2 H2 goes to N2 and 2 H2O. The overall equation, you just add the elementary steps together and you have the overall. Get rid of things that are the same on both sides. This is the overall equation. Look at our rate law. Our rate law has N2O2 in it. Do we have N2O2 as part of the overall reaction? No. No, we don't. That's a problem. You can't write the rate law on the basis of something that is not part of the overall reaction. Now, especially with N2O2, N2O2 is formed here and it's used up here. N2O2 is an intermediate. We can't write a rate law on the basis of an intermediate. So what do we do? Well, this is where we'll end today. What you do for something like this is we look at the step up here. We look at what we have up here. This is a fast equilibrium. See how we have the arrow going forward and the arrow going reverse? You have K1 going forward, K minus 1 going reverse. This is what equilibrium means. And we've talked about this a little bit before. Equilibrium is a state of balance. It doesn't mean that these are the same concentration. It means that this is going forward at the same rate it's going reverse. So for every 2 molecules of this that form one of these is falling apart into 2 of these. So it's dynamic, it's moving at the same rate. It doesn't mean these concentrations are equal. So we can write, because of that principle, we can write this. We can write that the rate forward, the rate law for the forward reaction up here rate is equal to K1 times the reactant squared, because in the elementary reactions, the coefficients become exponents only for elementary reactions like this. So this is the rate going forward, K1 times this. But this is going back at the exact same rate. So this is equal to K minus 1 N2O2. Now, is NO part of the overall reaction? Yes, it is. NO is part of the overall reaction. This is not. So by having a fast equilibrium, we know that the rate forward is equal to the rate reverse. And so now what we can do is solve for this guy in terms of everything else. Do we need to know what the exact rate is? No, we just know that whatever the rate forward is equal to the rate reverse. So we'll solve for this. Is equal to K1 all over K minus 1 times concentration of NO squared. Now what I know, I have defined N2O2, I have defined this thing in terms of something that's part of the overall reaction. So what I'm going to do is erase this. Give myself a little more board space. And when we do the substitution, we're going to plug this term, everything here goes right in here. So the rate is equal to K2 times K1 over K minus 1 times NO squared. That is what we substitute in for this times H2. We're almost done. How are you doing so far? Perfect. Okay. So now we take all three of these, because these are just constants, they're just numbers. The rate is equal to, we'll call this generic K, times H2. So our overall reaction, or our overall rate law, the rate law for this reaction, it's second order in NO, first order in H2, third order overall. Okay, beautiful. We will see you on Wednesday.